This is the lecture about dependent t-tests. So we'll go ahead and get started. Let's go through the difference between independent samples and dependent samples because you need to have this really clear. In independent samples, the data from one sample have no relationship to the data from another sample. The differences are just randomly spread through the groups. And they're sometimes even sampled from two different populations, for example, the boys and the girls. With dependent samples, however, the data are correlated and they have a relationship with each other. Each score generally has a parallel score. Usually it's the same population that's being tested twice or matched somehow, for example, a pre-test and a post-test. So the null hypothesis for independent samples says that the populations that these came from, that the means on this particular test or score or whatever will be the same, that there's going to be no difference in them. However, with dependent samples, we're saying that the difference is in the population, there's not going to be a difference in the population. Remember, there are not two groups. So it's the group being tested again or an equivalent group being tested. And this delta means change. So where over in the independent samples where we're talking about differences in means, in the dependent samples we're talking about a change in the means. Remember that the null hypothesis is always for the population. We distinguish that we are using a sample with a small d for the difference of the means. A caution. The small d with the bar over it means what is the difference between the means in the two data sets? What's the change? It does not mean what is the average of all the differences. Mathematically, there is a distinction. So the test statistic looks like this. So we need to know how to figure out the standard error for the difference. We don't have to pool the variance because we are working with one population. So we use either the differences formula or we use the raw scores formula. To find the standard deviation, which is always the first step, we take the square root of either the differences formula or the raw scores formula. So let me back up here. The variance comes first. We figure that. Then to get the standard deviation, we're going to take the square root of it. And finally, we're going to divide that standard deviation to get our error by the square root of the sample size. Nothing else in the procedures changed. So let's do an example. Let's pretend I randomly took 10 children from a 4th grade classroom and gave them a pre-test. After teaching the unit, I gave the same children the post-test to see if they learned anything. And here are their scores. I want to know if there's a statistically significant change between pre and post-test with my probability set at 0.05. First of all, let's be clear that these two sets of scores are dependent. Notice that each child took a pre-test and then has a corresponding or paired post-test score. The two data sets are correlated. In fact, the correlation is very high at 0.84. I'm going to assume homogeneity of variance because it's the same children. I usually approach these problems by gathering all the information I need first. Then I just quickly run my statistics and do the computations. So I'm going to be testing the difference in means, the change in the means, so I need the means for each test. The mean on the pre-test was 73.20 and the mean on the post-test was 81.40. The difference between the two means is 8.20 points. That's what I'm going to be testing to see if it's statistically significant, that change. I need the difference between each student's pre and post test because I'm going to have to figure out the variance and the standard deviation for the difference in order to get that standard error, the mean, for my denominator. So I'm going to record what the difference is in each child's test scores. So Bill, his difference was 9. Melissa's was a -3. Allie's was a +16, and so on. I'm also going to need to square these differences. So I square each one of them. 9 squared is 81, 15 squared is 225, and so on down. Now in my formula, I know that I need to add these up. I'm going to need the sum of the differences, and I'm going to need the sum of the differences squared. I know that my n is 10 because I have 2 sets of scores for each of 10 children. My n is not 20 with the dependent test. I have 10 subjects, and I've got everything I need to actually calculate my test statistic. So if I look at the raw score for variance, remember that's the first step. I'm trying to figure out what my denominator is going to be. You can see that I need the sum or the total of the differences and the sum of the squares of the differences. I know my n is 10. I'm going to need the sum of all those differences squared, and I'm going to need to square the sum of all the differences. I've got everything that I need, so I'm going to do that quickly. I'm going to replace each piece. I'm going to go ahead and figure those out, and keeping order of operations in mind. And I find out that the variance for that change is 83.73. Now I need my standard deviation for the differences. Well, to get standard deviation, all I do is take the square root. I took the square root of 83.73. And now to find my standard error, I divide the square root by the sample size. And that gives me 2.89. So let's see where we are so far. I have the pre and post tests scores for 10 children. I've got the difference or the change of 8.20. I've got the standard error of 2.89, and I know what my probability level is. So now I'm ready to go through the steps and do the actual testing and come up with the t-statistic. Step 1, I state my null hypothesis. My null hypothesis, you'll remember, says that in the population there will be no change. The change will be 0 from pre to post test. Step 2, I set my criterion. So I'm going to figure out what my critical value is. I have 9 degrees of freedom because I have 10 subjects, and my level of significance is 0.05. So my critical value is 2.262. In other words, my test statistic has to be above 2.262 plus or minus 2.262 in order to reject that null hypothesis that there's no change. So I compute my test statistic. I just put the right amounts in the terms, and you can see I've color coded them so you can quickly see where I got them from again. And I find out that my test statistic is 2.83. Step 4, I have to use the test statistic to accept or reject the null hypothesis. My test statistic is larger than my critical value, so I'm going to reject my null hypothesis. Finally, I'm going to interpret my results. The mean for the pretest was 73.20, standard deviation 15.99. The mean for the post-test was 81.40, standard deviation 11.87. The difference or the change in means of 8.20 was statistically significant, T, 9 degrees of freedom, equals 2.83, p less than 0.05. Or I could say the difference between the pretest and the post-test, or the change between pretest and post-test of 8.20 points was statistically significant. T, 9 degrees of freedom, equals 2.83, p less than 0.05. It doesn't matter so much how you say it, but you need to have these pieces. You need to tell what the difference in the means or the change in the means was. You need to give the test statistic with its degrees of freedom, and you need to give a probability statement. So to wrap this up, whether you're using independent samples or dependent samples, the pattern is the same. We start by figuring out the standard error because we're going to need it in the denominator for either test statistic. Always set your probability before you start. Remember that 0.0 is frequently used in educational research. Then you state your null hypothesis. Remember that the null hypothesis is for the population or populations. When you set your criterion for rejecting the null hypothesis, always keep in mind your n. With dependent samples, remember your n is the number of cases. And if you have 15 children each taking 2 tests, the n is 15, not 30. Finally, you compute your test statistic for the difference or the change. And finally, you use that test statistic to accept or reject the null hypothesis. If your test statistic is much larger with absolute value than your critical value from step 2, you reject the null hypothesis. Finally, you interpret the results, giving the reader the information that you found.